something called the central limit theorem. And this is how to normalize samples. And so with this concept, we will be using a formula that's very, very similar to the formula that you used when you found z-scores for the problems that you used in lesson 6.2. The idea here, though, is that we have a sample and we need to account for that. So when we find z-scores and when we find probabilities using a sample of data, there's some rules, first of all, and hold on a second, we're going to pause this. There we go. Okay, so first of all, when we normalize something, what we're doing is we're taking a number of samples, and every sample has its own sample mean. So if you look up here, if we were to take, say, 100 samples, meaning that we would go out and we would survey 30 people 100 different times, and then we would collect all of those sample means, and we use and then we can create a distribution with those sampling means, meaning we have a mean of a mean. I know that sounds complex, but so a sampling distribution of sample means is a distribution that uses the means computed from all the possible random samples. Now this works really, really well in a lot of science places where you have several different scientists taking data from all kinds of different things, and then you can normalize your data so that you can actually come up with some real conclusions that mean something. Now, we know that there is, anytime you have a sample, the answer is not going to be exact. It's not going to be perfect. So we have what's called a sampling error. So since we have a sampling error, we have to account for that. So the two things that are, hang on, we'll go back here really quick to we talked about most of this, but properties of the distribution of sample means, which is what we're going to be dealing with. So some of the things that we will, I lost the word, we will assume is that the mean of the sample means will be the same as the population mean. Okay, now obviously that's not going to be perfect, but that's what we're going to assume. And the standard deviation of the sample means will be smaller than the standard deviation of the population. So that information is just for you. It's not totally important for what we're doing. So central limit theorem says that if that the bigger our sample, okay, the less error that we're going to have. So when we so it says if a sample size is sufficiently large, the central limit theorem can be used to create z-scores much like we did in with a normal distribution. So we're going to assume that it's normal. Use this formula here. You notice the difference here. The x bar, this is the mean of the means, minus the actual population mean, which is given to you, divided by the standard deviation divided by the square root of n. Be really careful on a calculator when you're doing this, that you're putting parentheses and things in, otherwise it's going to mess up when it says calculations. So this is really all that's new today, is the idea of this formula. So let's go do an example. A survey found that the American family generates an average of 17.2 pounds of glass garbage each year. Assume that the standard deviation of the distribution is 2.5 pounds. Find the probability that the mean of the sample of 55 families will be between 17 and 18 pounds. So we want to find the probability that the mean will be within this range. So we take the mean, or the value that we're looking for. We're saying that the mean is going to be between 17 and 18. So this one we'll actually do twice. This is just like what we did last time, except we have to take into account that we're doing a survey population. So we're looking for the probability that it's in between these two sets of data. So over here, we're going to go 17, somewhere in here. I know I did this. I went a little slower than I had anticipated. So 17 minus 17.2 divided by 2.5 divided by the square root of 55. So, and I would put that in a calculator and get that number. And I would also go 18 minus 17.2 divided by 2.5 divided by the square root of 55. So we put these in a calculator, and they're going to give us z-scores so that we can look it up on the chart to find the probability that the mean of the sample will be between these two numbers. So once I get that, since I have these two values, one's on this side, one on that side, they'll add them together. So the z-score for 17 is negative 0.5933, and the z-score for 18 is 2.37. So the area for each of those in the chart, the area for negative 0.5933 is 0.2224. I think I was having an issue with my marker. Hopefully it will show up. Okay. So 0.2224, and then the area for 2.37 is 0.4911. And then I add those together, and I end up with 0.71. So the probability that if I were to survey 15 families, and that the probability of the means would be between 17 and 18 pounds is 71%. Now, example 2. The average teacher salary in New Jersey is $52,174. Suppose the distribution is normal with a standard deviation equal to 7,500. What is the probability that a randomly selected teacher makes less than 50,000? Now, keep in mind that this has nothing to do with sampling and surveying. Okay, so the very first thing that we're going to do is going to take us right back to what we did in 6.2. This is not a sample or survey, or it's not of samples. So when we use the formula, we don't divide by the square root of n because we don't have a number of, data for it. So in here we do less than 50,000. So we do 50,000 minus the mean, 52,174. We try to get our z-score, divided by the standard deviation. 7,500 is going to equal negative 0.2898. Okay. Then, if I were to look that up in the chart and get the area, the probability that a single teacher makes less than $50,000 a year, I look it up on the chart and I end up with 0.1141. When I was recording this, I'm sorry, I did this a while ago, that I was having issues with the pen. So 0.1141, but I have to subtract that from 0.5 because I'm looking for the tail, not in between here, and I get 0.3859. So there's a 38.59% chance that a teacher will have a salary of less than 50,000. Now let's sample and say what's the probability that the mean will be less than 50,000. So this is a different question. It's not asking what's the probability that a teacher will make less than 50,000. But what's the probability that if I were to sample 100 people, the mean would be less than 50,000? So I do the same thing, 50 minus 52,174. But now I have to divide by the square root of 100. And I calculated that, and I get negative 0.2898. All right. In the chart, now it's the same chart, the same picture. The picture has not changed. So I end up with 0.4981 once I look it up in the chart. Okay. And again, I have to subtract from 0.5 because it's a tail. So I subtract from 0.5 and I get 0.0019. So I have a less than 1% chance, in fact a 0.19% chance that the probabilities will be between, the probability that if I were to sample 100 teachers, it would be less than 50,000. So the probability that a single teacher is less than 50,000 is 38.59%. The probability that the average of 100 teacher salary is less than 50,000 is 0.19. So those are quite different. Alrighty. So moving on, you have a practice problem. Okay. So with the practice problem, I want you to pause, try it on your own, and then I will explain the solution after that. So go ahead and pause it. Now hopefully you've come back. It says A.C. Nielsen reported that children between the ages of 2 and 5 watch an average of 25 hours of television per week. Assume the variable is normally distributed and the standard deviation is 3 hours. If 20 children between the ages of 2 and 5 are randomly selected, find the probability that the mean of the number of hours they watch will be greater than 26.3. So let's look at the solution. Okay, we're going to move this. Okay, there we go. All right. So since the variable is normally distributed, we're going to the mean of 25. Okay, this doesn't matter up here. I'm sorry, this is just it's telling us, it's taken into account in the formula down here. You don't need to worry about this. So we draw a picture. 26.3 is greater than 25. And then we use our formula right here. And we end up with a z-score of 1.194. So 26.3 minus 25 divided by 3 over the square root of 20 is 1.94. And if I can get off screen, hopefully I can, there we go. So the area between 25 and 26.3, or 0 and 1.94, is 0.4738. Subtract from 0.5, so it's 2.62%. So the probability that if I were to survey 20 of them and it would be greater than 26.3 is very, very rare. And that's the end. We'll talk to you tomorrow.